gas chromatography, and we said that gas chromatography had to do with the mobile phase that is made of gas. So now we want to just briefly look at high performance liquid chromatography. And we know that in this case, the stationary phase and your mobile phase is made of liquid. And we would also look at the schematic and the instrumentation of HPLC. So HPLC is a form of liquid chromatography that is used to separate compounds that are dissolved in solution. And the instrumentation of HPLC consists of a reservoir that is made of your mobile phase. There is a pump, an injector, a separation column, and a detector. So while this occurs, the compounds are separated by injecting a sample onto the column. Just as you have your GC column, there's a column here, and the different components in the mixture are made to pass through the column. They are differentiated by the differences in their partition behavior between the mobile phase and the stationary phase. So what separates is the partition between your analytes in the mobile phase and the stationary phase that brings about the differences in their separation. So we already know that the mobile phase in high performance liquid chromatography is a liquid, and the liquid that is used as the mobile phase is called the eluent. The stationary phase can be made of solid or an immobilized liquid, just like in your gas chromatography, you have gas solid chromatography and gas liquid chromatography. And we say that the gas liquid chromatography is whereby your stationary phase is an immobilized liquid. So also in HPLC, we have the stationary phase can also be made of solid or liquid. But in general, any substance that can be dissolved in the mobile phase can be used as any sample that can be analyzed should dissolve in the mobile phase, and that is the major requirement or prerequisite for the use of HPLC. So your sample should be suitably dissolved in the mobile phase. So what are the advantages of high performance liquid chromatography? Remember when we're talking about GC, we said GC is only suitable for volatile compounds. That means the compound should be able to volatilize in the column and be able to be separated as the gas mobile phase is carrying it. So HPLC offers some advantages over gas chromatography. And also for GC, I can't remember if I mentioned that GC can only analyze small molecules. Any molecule that has atomic size beyond 500 atomic mass units, you can't analyze them with GC. And that is why GCs are not useful for macromolecules like your proteins, nucleic acids, carbohydrates, sugars that have high molecular mass. So this gives HPLC some advantages over GC. So this HPLC has high separation capacity. That means it enables batch analysis of multiple components. It has superior quantitative capability and reproducibility. There is unlike GC, the sample does not need to be vaporized. It has high sensitivity, low sample consumption, and you can use it for separation and purification of samples. So in comparing HPLC to GC, the LC can be applied to separation of any compound that is soluble in liquid phase, like I said before, and it is usually more applicable to biological compounds, whether they are synthetic or natural polymers or inorganic compounds. The liquid mobile phase allows the liquid chromatography to be used at lower temperatures. So unlike the GC, whereby you have to vaporize your samples, you can work on at low temperature. So liquid chromatography is better suited for separating compounds that are thermally labeled. So any compound that can be affected by temperature, HPLC will be better for separating them than GC. Then the retention of solids in liquid chromatography is dependent on the interaction with both the mobile phase and the stationary phase. Remember, for GC, the stationary phase had nothing to do. The mobile phase had nothing. Your gas was inert and does not react with your solutes or your analytes. What was where the interaction was taking place was at the stationary phase and your analytes or your solutes. But for liquid chromatography, your analytes of interest will interact with both the mobile phase and the stationary phase. So in GC, retention is based on volatility and interaction with the stationary phase, while in liquid chromatography, there's lots of optimization that can be carried out either on the mobile phase or stationary phase. And unlike the GC, whereby we had just limitation in the type of gas we use, you use just your maybe helium, nitrogen, or argon for gas chromatography, stationary, mobile phase. In liquid chromatography, there's a wider array of substances or solvents that can be used as your mobile phase. So that gives more flexibility in optimizing the condition for the liquid chromatography. And in GC, some detectors, as we saw, were destructive, like your flame ionization detector. Once your eluent goes into the detector, that is the end. You can't recover your solute once it gets into a destructive detector. But for liquid chromatography, most of the detectors are non-destructive. So meaning that you can recover your sample at some point, maybe to do more analysis. For example, when your sample gets to the detector, you can collect that fraction and probably maybe work on it and do, maybe you want to do your NMR analysis or infrared analysis on that particular eluent that you have collected. So you can use it for further elucidation after your chromatography. So now in HPLC, the retention and elution of solutes depends on the interaction of your solutes with both the mobile phase and stationary phase, as earlier said. So your elution can be described by how well your analytes or solutes are retained on the column. So with different solvents, the interaction of your solutes on the same column using different solvents will be different. So that is how you note what your interaction. So you could actually use the same stationary phase, but different solvents, and you get different interactions entirely. Who is that is writing on the slide? So your interaction of your solutes on the same column will be different if you use different mobile phases. So the instrumentation, like I said, we're not going to be going in depth into HPLC like we did for GC. So this is your solvent reservoir. Then you have a pump, because the solvent is going to pass through the column using a pump. So your solvent passes through the pump and it goes and flows into the injector. This is where your sample is injected. So you inject a sample into the stream of the mobile phase, just like you also inject into your stream of your gas for GC. In HPLC, your sample is also injected into the stream of the mobile phase. You have your column that is also sitting in an oven, and your sample flows through the column. Then from the column, it goes to the detector. And from the detector, since it's a liquid that is flowing, you can collect your waste at the end of the detector, and you have your computer that processes your data. And like I said, this sample, you can collect different fractions. Let's say at 2 minutes, there's a particular fraction that gets to the detector. You can put a vial there and collect that fraction. Then maybe your chromatogram shows another analyte reaching the detector at another time. You can place different vials and collect your different fractions at different times that they are collected from the detector. So you have this is the picture of a modern HPLC. So your solvent reservoir is at the top here. So there's a cabinet here where your solvent is. There is like a PC that controls the flow rate of your mobile phase. Then you have a degasser. There's a degasser here, and the purpose of the degasser is that you don't want any bubble inside your solvent, because if there's a bubble in your solvent, the bubble or the air that is trapped there would also be detected by the detector. So the bubble, you don't want a bubble in there. So that is why there's a degasser that is placed here. Then you have the pump, because there's a peristaltic pump that controls the flow of your mobile phase as it's flowing there. Then here you have your sample injector, whereby you have an auto sampler, just like we had for the GC, that picks your sample at different times. And as your mobile phase is flowing, it flows into the auto sampler, and your injector is right in here. Your sample is injected into that, and it goes into the oven where you have your column, and from the column it flows into the detector, and that is where your chromatogram is picked from. And on the screen here, you have your chromatogram as it is separated from the column. So you have inside your solvent vial, there's a filter there, and the filter is usually made of stainless steel, and because you don't want any particulates from your solvent to get into your detector. So there's a filter that is usually at the end, at the base of your reservoir, that filters what goes into the tubing. So this is your tube that your mobile phase travels in. So there's a frit at the end of this tube, and that's where you have a filter that removes any particulate from your solvent. Remember, if there's any particulate in your solvent, once it gets into the detector will pick it as one of your solutes, and you don't want that to be as an interference. And also, when your sample is injected, you have what we call the pre-column filter. It's also whatever escapes here and goes into the injector is also trapped in the pre-column filter. And after the pre-column filter, you have what we call the guard column. The guard column is similar to your analytical column that would also remove any unwanted material before you get into your analytical column where the separation takes place. So all these are just the quality assurances for the removal of particulates from the sample, so that you don't want your auto sampler to be damaged, or you don't want your column to be damaged by any form of particulate that is present in your sample. So these are the major composition of your HPLC system. You have your solvents, the solvent delivery system, the injector, the sample, the column. Then you have detectors, you have the waste collector, and you have the recorder that records your chromatogram. So like just like your GC,
That's my charger for me.
is your column.
Tommy.
Mute your microphone. Who is that talking there? You've been told to mute your mic as you join the class. So the heart of the HPLC system is the column, and the column, just like your GC column, contains the particles, which is your stationary phase. And the mobile phase is pumped through the column by a pump. And that's why in your schematic diagram, you always see a pump there. So what the pump does is to pump your stationary phase, your mobile phase must pass through, because the column has a narrow diameter, and the pressure would the pump will have to generate the pressure that will allow the flow of your mobile phase through the tubes into the column. And like I mentioned before, the solvents must be degassed, so that you don't want bubbles formed in your stationary phase. So the solvent delivery system has three basic functions. You want to have a reproducible separation. So the solvent delivery system will provide an accurate and constant flow, because you have to monitor the flow rate. If your flow rate, you are pumping your mobile phase at 1 ml per minute, the interaction of your analyte will be different from you are pumping it at 0.5 ml per minute. So for you to maintain a constant flow rate, the solvent delivery system will be programmed such that the flow rate of your analysis will be maintained throughout. And also, the solvent delivery system helps to provide accurate mobile phase composition. We'll look at it later on. Your mobile phase, sometimes you work with mixtures of mobile phase. You could say 50% acetonitrile, 50% water, and you want to maintain that composition throughout the run of your sample. You make the solvent delivery system will make this achievable. And also, it also helps for the push of the mobile phase through the tightly packed column. Your column is already packed, and you want to run your mobile phase through the column. There will be pressure that will be generated, and it will hinder the free flow of the mobile phase. But when you use a solvent delivery system, it enables your mobile phase to be able to push itself through the tightly packed column. So we look in the air now at the role of the different mobile phases. So your mobile phase, your pump, the role of the pump is to force your liquid through the liquid chromatograph at a specific flow rate. So the pump will allow you to flow, will allow your liquid mobile phase to flow at a specific flow rate. And there are two ways your mobile phase can flow. The pump can deliver a constant mobile phase composition. We call that isocratic. Just like you have your isothermal temperature. Here in isocratic delivery, there will be a constant mobile phase composition. So I could just say all through my analysis, I want 70% water and 30% methanol. And that will be what will be maintained from the beginning of the analysis till the end. That is isocratic. So the mobile phase composition remains unchanged. Remember your isothermal, whereby your temperature remains unchanged throughout your analysis using the GC. So it's a similar process, but in this case, instead of maintaining a constant temperature, you maintain a constant mobile phase composition throughout your analysis. Or it could be by gradient. In gradient elution, your mobile phase changes during the analysis, just as we had for temperature programming, whereby your temperature programming changes as the analysis progresses. So we have the injector. The function of the injector is to introduce a sample into the high pressure mobile phase flow as a very small volume, and it should enter the column in as an homogeneous low volume plug. Because if you don't inject it as an homogeneous plug, there will be band broadening, and you have all the sorts of eddy diffusion that we looked at when we're looking at the theory. So we don't want your sample to enter the column at different times. So it must enter as a plug so that your sample would not have, your chromatogram will not be tailing or fronting. And also between your column and the injector, the distance between them must be minimized. You don't want the length of the tubing to be so long between the injector and the column. So you want it to enter the column almost immediately as soon as you inject. You know that for the HPLC, you also, for the GC, as soon as the sample enters the injector, it goes straight into the column. And it's the same thing we're also using for HPLC. So you don't want your sample to enter and travel a long distance before it enters the column. When that happens, you could have band broadening or eddy diffusion that we looked at before. So the injector can be manual, as we said before. So this is somebody injecting the sample into the injector of the HPLC, or it can be auto sampler. So the one on the right here, where you have my arrow, is the auto sampler. You can see several vials that are put on a tray. So the injector, there's a robot in it. You can see the tip of the injector. It goes there, picks the vial, and injects into the chromatograph, as we saw before for the GC. So the injector introduces your liquid sample into the flow of the mobile phase, and your auto sampler picks up the sample. So in the HPLC, we have two different phases available. We have what we call the normal phase, and we have what we call the reverse phase. In normal phase HPLC, your stationary phase is polar and your solvent is not polar. Remember when we're talking about partitioning, your phases, you must have two different phases. So your stationary phase is polar, your mobile phase will be non-polar. And just as we look at the principle of liquid-liquid extraction, where like separates like. So for normal phase, I'm asking a question now. What type of analytes would you separate using a normal phase? Is it a polar analyte or a non-polar analyte in normal phase? Remember, your stationary phase is where the separation is taking place. So what will you use for your, what kind of analytes will be analyzed by the normal phase? Polar analytes or non-polar analytes? Yes, I'm waiting for
polar analytes.
Analytes, because
Polar analytes.
like, thank you very much. The like would always separate like. So if your stationary phase is polar, the type of analytes that you also separate with that will be a polar analyte. Then the reverse phase, in reverse phase, your stationary phase is non-polar. And for a partition to occur, your solvent or your mobile phase must be polar. So, and for reverse phase, the type of analytes that you analyze in reverse phase will be non-polar analytes for reverse phase solutes or analytes. And just like we saw before, HPLC can also be applied to all the other forms of chromatographic separation. Remember the first lecture, we looked at partition, adsorption, ion exchange, and size exclusion. And we said for GC, it's only adsorption and partition that is applicable to GC. But HPLC can go beyond adsorption and partition. You could also have ion exchange, whereby the stationary phase will contain ionic groups and the mobile phase will be a buffer. Then size exclusion also can take place. You can also practice size exclusion chromatography using HPLC. And here, large molecules, the separation will be based upon the size of your molecules. And I said that large molecules will elute first, while smaller molecules will elute much later. So the injectors, we looked at the injector before. The injector places the sample into the column, and you don't want the length of the tubing to be long. I think we talked about this, about injectors. Then the column, which is the main key player in HPLC. So it's one of the most important components of the HPLC because the separation is achieved when the components pass through the column. So when you inject a sample into the tube, nothing would happen even when your sample is still flowing with mobile phase until it gets into the column. So the tubing of HPLC of the column is usually made of stainless steel tubes with an internal diameter between 3 to 5 millimeters and a length ranging from 10 to 30 centimeters. You can see here now that the length of HPLC is far shorter than that of the GC. GC column can be as long as 100 meters, while the length of the HPLC column ranges from 10 to 30 centimeters. And normally the columns are filled with silica gel, and because of the properties and the shape, the surface properties, and the pore structure of the silica gel. So silica can be used separates a wide variety of chemical compounds, and the chromatographic behavior for using silica is usually very predictable and reproducible. So this is how your column looks like. The outer part of the column is made of stainless steel, and inside of it is where you have your silica gel or your stationary phase. So these are different lengths of columns. This is about 30-meter column. This is 20 meters. This is about 10 meters. And you have your guard column also, which is made of the same material as the stationary phase in your analytical column. So now, what affects the system? The column parameters. So you have the instrument parameters, you have the column, the temperature, the flow, the signal, sample sensitivity, and the detector. So these are the instrument parameters that we can vary. You can change your detector, you can change the flow rates of your sample and your mobile phase. Also, your column can also be placed in the oven. Temperature does not really have much influence in HPLC, or like your HPLC where, or like your GC where your sample has to be vaporized. In HPLC, the temperature, your column is housed in an oven, so that there will not be differences or fluctuations in the response of your detector. So the temperature here is just to control. Sometimes you just want to put it at an ambient temperature, and that will be the temperature where your sample will be working at. Then the column parameters is that you look at the different stationary phases, the coating materials, and the material of the column. So this also can be varied, just as you can also vary the instrument parameters. You could also vary the column parameters as well. So we looked at different types of column types: normal phase, reverse, size exclusion, and ion exchange. So for normal phase, we are trying to reiterate what I've said before. The retention of the normal phase is governed by the interaction of the polar parts of the stationary phase and the solutes. So we know that in normal phase, your stationary phase is polar and your analyte is also polar, while your mobile phase is non-polar. Then in reverse phase, the column packing material is non-polar and the solvent is polar. So in reverse phase, now use solvents like methanol, acetonitrile, acetone. Water can be used as the solvent for the reverse phase, while the stationary phase can be, they are usually non-polar hydrocarbons like your carbon C18 or C8, and the solvents are usually polar aqueous organic mixtures such as methanol and water, or acetonitrile and water. So you can mix your mobile phase, varying different compositions of your solvents. So size exclusion, the HPLC column is consisted of substances that have controlled pore sizes. So the pore size determines the type of interaction your analytes have with the stationary phase. So, and in this, like I said before, the large molecules will always elute before the smaller molecules. And also for ion exchange is a separation that is based on the interaction of your analytes with charges. So the components are separated based on attractive ionic forces between the molecules carrying charge groups of opposite charge to those charges on the stationary phase. So now, in terms of the delivery of your solvent, I've said before that it can be, your mobile phase can be made to be isocratic, whereby you have constant composition of your mobile phase from the beginning of your analysis to the end. Or you have what we call the varying eluent composition, which is also called the gradient system, whereby you can start, let's say, with 100% methanol at the start, and after 5 minutes, you can reduce the methanol constituent by maybe reduce to 80% methanol and 20% of water. And also you could relate on that another 5 minutes, you can increase your methanol to 85% and water reduces to 15%. So that is what we call the gradient system of varying elution eluent composition. So the gradient elution, 2 or more solvent systems are employed. So the ratio of the solvent is varied in a in a programmed way, sometimes continuous, sometimes a series of steps. But another difference between isocratic and gradient is that in isocratic, you may have just one solvent. It could just be methanol all through, or you could have a mixture of solvents. But in gradient elution, it's usually a mixture of solvents that are programmed at different time intervals to be delivered into the mobile phase. So this is your isocratic elution. You can see here now that you have a solution of maybe 10% of B and 90% of A. And from the beginning of the run till the very end, your composition is maintained. Then for gradient elution, can be linear or stepwise. In the linear, it just starts here, and every minute there will be an increase in the composition of your mobile phase. Whereas in your the stepwise one, you have a series of isocratic levels. It will rise at a certain degree. Then you have anisocratic interruption, it rises. So you have different steps of isocratic and gradient elution curves. But just like the isothermal elution in HPL, in GC, isocratic mode can also give us very long analysis time and poor separation. So you can see that the samples are more, they are clustered, the chromatograms and the peaks are not well resolved, unlike when you have long analysis time and they are well separated and resolved. So this is there are 2 chromatograms there comparing isocratic and gradient elution of a particular sample, which is a mixture of 8 components. If you look at the bottom chromatogram, this is your the gradient elution, whereby the 8 components are separated very well, depending on their composition, whereby the top chromatogram is an isocratic one, and you can see all of them coming out at about the same time. So talking about detectors, we have different types of detectors, just like we have different types of detectors for GC. The most common one is your UV visible absorbance detector, whereby it works on the principle of absorbance of intensity of light, and whatever is refracted is now seen as a different chromatogram. So we have the UV visible absorbance detector, we have the photodiode array UV visible absorbance detector, you have the fluorescence detector, refractive index detector, evaporative light scattering detector, electrical conductivity detector, and mass spectrometer. So these are different types of detectors and their sensitivities. You can see here that the absorbance, whether it is HPLC, UV absorbance or visible, the sensitivity is up to nanograms, and it is possible for gradient systems. Usually, the fluorescence one, the fluorescence detector will only be useful for compounds that can fluoresce. So when your samples have excitation and emission wavelengths, you use the fluorescence detector. We have differential refractive index detector, evaporative light scattering detector, electrical conductivity detector, and electrochemical detector. And their sensitivity varies. Those that have up to picogram means that they're very selective and they can measure very, very low concentrations. So before you introduce your sample to the HPLC, you have to do some pre-treatment whereby you improve the accuracy of the quantitative values. You also increase the sensitivity of the values and the sensitivity of your instruments when you pre-treat, because if your sample is too dilute, your detector may not be able to see, but when it is concentrated, it becomes more obvious for your detector to detect them. And also pre-treatment is important so that you don't want your column to deteriorate. Remember I told that a GC column is very expensive, and also HPLC columns are also very, very expensive. And if you treat your samples very well, unwanted elements or materials will not get to your column, thereby spoiling your column. So what are the substances that must not be injected into the column? Substances like your microscopic particles and precipitates of your precipitation analysis, substances that can be precipitated in the eluent, substances that can irreversibly adsorb to the packing material, and substances that dissolve or chemically react with the packing material. You don't want this to go into your chromatograph. The sample can be, you filter every sample before injection. So you filter them and you get them disposed when you filter them before you get to your column. So this is the syringe and this is a membrane filter. So what passes through the filter head will trap the unwanted material and you elute whatever you need. So in handling this column, there are some restrictions that we must work. You must not allow the sample, your column, to go beyond a certain pH range, because HPLC you can use buffer solutions as your mobile phase. And so when you're preparing a buffer that has a very high pH or low pH, you don't want that to occur, because those high pH or low pH will degrade the components of your column. Then the packing material in your column, you must not allow them to get dry. Then any solid or microscopic particles are filtered before it goes into the column. Then you don't want to put so many load of your analytes on your column so you don't get your column damaged. So what are the problems that columns can have? Columns can be, if you filter your samples, you are preventing your column from clogging. So you must filter your samples each time before you introduce them into the HPLC, because if they're not filtered, the particulates in the sample might clog your column. So you don't want that. Then you rinse your column with appropriate solvents, and you connect your column in reverse and flush out. So if there's any debris sitting at the entrance of your column, when you reverse your column, it will exit immediately and you will have no interference in your column. So these are some problems that could happen using your HPLC. Your sample can be overloaded, so you reduce the sample injection and volume. For HPLC, we inject up to 20 microliters, unlike in GC where we only inject about 1 microliter. But for HPLC, we can inject as much or as high as 20 microliters. So also in HPLC, you don't want your baseline to drift, and your column also should be rinsed each time you finish an analysis. You rinse your column so that your column is void of any form of carryover of your analysis. Samples are, the column can also be stored in order to prevent putrefaction, alcohol, or other preservative substances. You have to store it very well that you don't have your column to degrade in the instruments. So HPLC, has been said before, is used for the chemistry and biochemistry research, analyzing complex mixtures. It can be used for purifying compounds, for developing processes for synthesizing chemical compounds, HPLC can be used for analyzing natural products or predicting physical properties. HPLC can also be used in quality control to ensure the purity of raw materials, to control and improve process yields, to quantify assays of final products, and to evaluate product stability and minor degradation. So HPLC, in addition to being used for analyzing air and water pollutants, it is also used for monitoring pesticide levels in the environment. You can use it to monitor some pesticides and also drugs of abuse. We can use HPLC to monitor them. Apart from that, it can also be used to survey food and drug products for identifying confiscated narcotics or to check their adherence to label claims. So we use it extensively by regulatory agencies to survey food. You can use that, they can go to sample food items and run it through HPLC to know what are the components or if there's any pollutants in your sample prior to use. So this is just a quick rundown of your chromatogram, your HPLC. So I don't know if any one of you has a question on that. Like I said, our major focus on this course is gas chromatography, but we just have to mention about HPLC so that you have an understanding of that as well. Any question?
I have a question, ma'am.
All right.
Okay, assuming I'm sampling, actually making just a sample. I don't know the composition of it. I don't know whether it contains maybe any metal or any particular metal that I know of. If I run it through, let's say GC or HPLC, and I get the chromatogram, how am I going to identify a particular peak and to label it to, or to pin it down to a particular analyte that I'm looking for? Or if I see several peaks, how am I going to identify that maybe this one is a particular analyte and this one is maybe any other thing at all?
Okay, thank you for that question. Still, it's the same principle that we had for GC. When we are doing analysis, either by chromatography or spectroscopy, we work from known to unknown. Let's say I have a water sample, for example. I have water, I want to analyze this water bottle I'm holding. I'm having this water, I want to note maybe pesticide residues in this water. And I have to analyze it by HPLC. The first thing we did when we started this lecture is that I have to first do my liquid extraction. I will extract it using a suitable solvent to extract the analytes of interest here. Now, after analyzing, who is that? Mary. So after doing my liquid extraction, I will extract. I may not be able to see the components of my solids, but I can use liquid extraction, extract it into a suitable solvent. I can extract this and now concentrate it and make it into maybe 1 ml. So that 1 ml extract, maybe into dichloromethane or hexane, is my extract. Now, to quantify what I have, if I'm looking for a particular pesticide or maybe drug residue, I will now procure what we call standards. I will prepare my standard in different concentrations. I can prepare 1 ppm of my standard, 2 ppm, 4 ppm, 8 ppm, 10 ppm. The standard that I know the concentration, I will inject it into my HPLC. So I will start by injecting standard 1 of 1 ppm. It will give me an area. So I will have a table of my concentration and peak area. I will inject standard 2, get the peak area. Inject standard 3, get the peak area. Inject standard 4, and you know that your peak area is directly proportional to concentration. So as concentration is increasing, your peak area is increasing. Then I will now plot a graph. I'll plot a graph of my concentration, against my, if this my x-axis is my concentration, the y-axis is my peak area, and I plot that, I will get a linear graph, which is similar to what you did with your BS law. So now this is my concentration on this axis. This is my peak area on the other axis. So now I get what we call a calibration plot, which is a plot of concentration versus peak area. Now my sample that I've extracted, I will inject it into the HPLC. I don't know the concentration, but the HPLC is able to give me the peak area. So the peak area that the HPLC gives me, I will note the peak area. Then I'll come back to my calibration. Let's say the peak area is something over here. So I will now extrapolate on this calibration plot and come down, and whatever I see here will now be the concentration of my unknown sample. So in looking at what you have there, you always start with your known sample. So the known sample will give you the peak area, and from there you can extrapolate the concentration of your unknown from the peak area that you already know from your sample. I know whether I answered that question for you.
Yes, you've answered part of it, but can it also be used like qualitatively to determine the identity of a particular peak?
Yes, we also you can use it for qualitative analysis, but that is why we have our detectors. So the detector, for example, if I'm working with chromophores that will absorb at a particular, I can set my detector to 254 nanometers, and all the chromophores there that can be detected at that wavelength will be detected. If there are compounds that can fluoresce, I can also set the emission and excitation wavelength of my analyte, and the elution pattern will be the same. So let's say component A elutes at 5 minutes, then at 10 minutes component B elutes, at 25 minutes component C elutes. So that even without quantifying them, I can know what pattern of analytes that are eluting at different times. So let's say at 3 ppm now, at 3 minutes, there's no component eluting, and I inject my sample. None of my standard had an elution time of 3 minutes, and I inject my sample, and at 3 minutes there is a chromatogram. That means that it's not what I'm looking for that is eluting at that particular retention time. Is that clear?
Okay, thank you. I also want to ask something else, please.
Okay.
Now, since there are so many variables that can be like manipulated for all this chromatographic technique, from GC, temperature, and then since there are so many things that can even affect the retention time, is it possible for me to convert from one particular retention time, assuming I'm like comparing two results from different laboratory, or even two different analysts, or even using two different conditions? If I'm now having two different results, two different chromatograms, is it possible for me to convert from one to the other, or to shall have something that is comparable if I'm having two different results, or even if I'm using two different instruments to measure them, because so many things can affect it. So if I know the particular variable that I'm manipulating, maybe in a particular instrument, is it possible for me to change the result, like to convert it into a different result if I'm using a different instrument?
You can't use the same, you can't compare. The basis of comparison will be that you have used the same flow rate, or you have used the same gradient elution. You can only compare similar optimization. You can't compare, maybe use a 30-meter column, a 30-centimeter column, and your mobile phase was acetonitrile. Tomorrow you use a 10-centimeter column and use methanol and water. The results will not be comparable. You can only compare when you use the same and identical conditions in your instrument. And now if you look at any journal where they've used HPLC or GC, that analysis, the scientists will tell you the name of the column, the length of the column, even the internal diameter of the column, the thickness of the stationary phase, the temperature, so that if you see maybe a journal that you want to replicate, you have to follow the precise conditions that author has used. So in that case, you use different methods and compare them, you won't get the same results. So for you to compare, the two results must be the methodologies that generated the two results must be identical. So you can't change. Just like in your GC, you can't maybe today you use a polydimethyl siloxane column to do your analysis. Tomorrow you now want to use a 5% phenyl dimethyl siloxane. You won't get the same result because the interactions would be different. Remember that it's the interaction that brings about separation. So if they have different interactions, they will have different separations. I hope I've answered your question.
Yes, ma'am. Thank you.
Okay, so now let's also quickly revise the comparison between HPLC and GC. In HPLC, you don't need any compound to be volatile. The volatility is not requested in this. Now, in terms of volatility, we said for HPLC, for GC, you need volatile sample. For HPLC, your sample does not have to be volatile. The requirements that you need for HPLC is that your sample should be soluble in the mobile phase. That's the major requirement. But while for GC, sample must be volatile. Then in terms of sample polarity, HPLC can separate both polar and non-polar compounds. It can separate inorganic ions and organic ions. But GC is only can only separate non-polar and polar compounds. The samples are non-polar and polar. HPLC, it can be homologa. So that's a basis of comparison for that. So whereas you look at GC looks at volatility, and HPLC, the volatility of your sample. In terms of thermal lability, your HPLC can take place at room temperature or below room temperature. While GC, your sample must be able to survive high temperature injection at the as well as high temperature for the column. So you note here now that for HPLC, when a sample is thermally labeled, that is, can be degraded by high temperature, GC will not be advisable or suitable. You use HPLC. Then in terms of molecular weight, there is no upper limit for the molecular mass of your sample that you analyze with HPLC. There's no upper limit. There's no size, no dimension of your sample. The only limit for HPLC is solubility. Meanwhile, for GC, samples that have high atomic mass units will not naturally be able to be separated by GC, because you know that we talk about volatility, and the higher the molar mass, the lower the higher the mass, the lower the volatility. So, and that is why for this we will only use GC for samples that has to vaporize. Any questions so far?
Excuse me, ma.
Yes.
We're saying something about isocratic and gradient system. So in that gradient system, I saw something about high pressure and low pressure.
Yes, it depends, or you can do some. There are some, you can use high pressure, you can use low pressure. The instruments.
So I want to ask, what's the relationship between?
It depends on the packing of your stationary phase. So if the stationary phase has a very tight packing, you will need a high pressure to achieve that. So it depends on the methodology you are doing. So some instruments are able to do just high pressure, And some, if the pressure becomes high, there will be back pressure generated, and you'll not be able to have an efficient separation. So the two of them is just the instrument specification. Is the instrument specification that will do that. Do you understand? Any other question before we proceed?
I have a question,
Yes.
but it's actually on detector.
On the
Yeah,
Okay, ma'am.
it's actually on
Huh?
detectors. We were talking about detectors today, and I remember that in our class on GC, gas chromatography, we also talked about ID detector. And one of the characteristics that was mentioned was non-destructive of sample. And then
yes.
on that GC, we listed some types of detectors, like the flame ionization detector and all. And the flame ionization detector was actually destructive, while
Yes.
the thermal conductivity detector and the electron conductor detector, they're actually not non-destructive,
Electron capture detector. Electron capture detector.
destructive. Okay.
Yes. You
So I
say
actually wanted to ask that what does it mean for a detector to be destructive? Because in a class, detectors are actually non-destructive.
what I mean by that is that for a detector to be destructive, it means that you can't recover your sample again. You can't recover your sample again when it is destructive. You can't recover it. But you know, with the way HPLC is, I wish I could look at an instrumentation here. So look at what we have here on this. This is a slide by Agilent. You have your mobile phase pumped. There's a mixer that mixes the different ratios. Your sample is injected, and in between your injector, immediately goes into your column where separation takes place. And at the exit of the column, it goes into the detector, and the detector will be able to tell you your analyte that was detected. But let's say once my analyte gets to the detector and I find out that I can see a chromatogram, as soon as I see a chromatogram, once it gets into the detector, it goes into the waste. I can collect, let's say at 7 minutes, I'm interested in maybe I have a mixture of 3 components and I inject. And when the 3 of them get into the components, after 5 minutes, component 1 comes out. After 10 minutes, component 2 comes out. After 15 minutes, component 3 comes out. And I'm interested if I want to run the IR of component 2. Once the detector shows on the screen that component 2 has been eluted, I'll quickly come here at the bottom of this place, put a vial and collect that fraction that as it's flowing out. Maybe I want to do NMR of it, I want to do IR analysis, so I can recover. But in a destructive detector, once it gets into this place and is destroyed, I can't retrieve my sample again. That's what we mean by being destructive and non-destructive. So almost all HPLC detectors are non-destructive because in actual fact, you can collect your sample, retrieve it, a fraction of your sample that you have separated, and maybe you want to do thin layer chromatography, or you want to do further elucidation of that, you can always do that with it. Do you understand? But for FID,
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
there will be a destruction, you can't recover it again. That's the difference between that. Then still talking about the comparison between HPLC and GC. In terms of sample preparation, for HPLC, the sample must be filtered and the sample should be in the same solvent as the mobile phase. See, my mobile phase is acetonitrile. My sample must also be in acetonitrile. Unlike in GC, I can extract in one sample Hello, can you hear me?
Yes, ma. You can hear
Yes,
you, ma.
ma.
And my internet went off briefly. So the sample must be the same solvent. So now look at it as an example whereby, let's say I'm extracting pesticides from water and I use N-hexane. N-hexane, is it polar or non-polar?
Non-polar.
Non-polar.
N-hexane is non-polar. So, and let's say I want to use reverse phase chromatography. What type of mobile phase will I use for reverse phase? Reverse phase?
Non-polar.
No. What
Polar
type of
solvent.
mobile phase?
Polar.
Okay, polar. Yeah, it's
Polar.
polar.
So, but while I was, remember when we did liquid extraction, we said like would dissolve like. I've used N-hexane, which is non-polar, to extract my sample. And my sample is non-polar, and I use hexane, which is non-polar. Now, you remember that for reverse phase, my stationary phase must also be what? Non-polar. And my mobile phase must be polar. And one of the requirements is that your sample should be in the same solvent as the mobile phase. So what do? I have to transfer my analytes from that non-polar solvent to what? A polar solvent, which is my stationary phase. So what I will do is that I will dry my solvent, bearing in mind that my solutes must not escape. So I can use nitrogen to dry the solvent and reconstitute in another solvent that is compatible with my stationary phase. But the rule is that your sample should be in the same solvent as the mobile phase. But for GC, the sample must be volatile and must have lower boiling points. Your solvents must be volatile that you introduce into your GC and must have lower boiling point than your analytes of interest. And in terms of sample size, we can introduce large volume of injection up to 20 microliters for HPLC. But GC, we introduce very small sample, typically between 1 to 5 microliters. So your sample that you're introducing is smaller for GC. For HPLC, we can introduce up to 20 microliters for GC, for HPLC. Then in terms of separation mechanism, in HPLC, both the stationary phase and the mobile phase take part in the separation, because that's why we said that your sample must be soluble in your mobile phase and the stationary phase does the partitioning of the separation. Whereby in the GC, what does the separation, the mechanism of separation is just the stationary phase. The mobile phase is inert. It only carries your sample into the stationary phase where the separation will take place. And also in terms of detectors, HPLC, the most common detector is HPLC is UV visible, and we have a wide range of non-destructive detectors. We have your the three-dimensional detectors like your mass spec. We have detectors that have that are highly sensitive up to very sensitive detectors. But GC, the most common GC detector is a FID, which is a destructive detector, and it is universal to organic compounds, just like your UV visible is also universal to most chromophores that will absorb in the UV visible region. So it's an example that contains these different carbohydrates so you can this was detected using acetonitrile water mixture, 70% acetonitrile, 30% water, using an ammonium column with a length 250 millimeter length and 4.6 millimeter ID. And the flow rate was 1 mil per minute. And the detector is a refractive index detector. You can see the chromatograms as they are separated. But like I said, for you to know the elution pattern, you use standards. The standard will tell you when you inject a fructose standard, it will have its own retention time. Glucose will have its own, sucrose will have its own, lactose will have its own, and each of the carbohydrates will have their own specific retention time. So if I do the standard and I do this, so when I inject my sample, for example, and I only see a peak at this retention time, I'll just compare with that of my standard. I will do that, oh, it's only sucrose that is in my sample. If I inject and I only see peaks at 1 and 6 retention time, I will know that it's only fructose and isomaltose that are there. But for you to be able to know from your unknown, you have to first inject your sample, which is a known standard. So this is your, I'm playing a video now, you can watch the video. As the sample is injected, as it gets into the detector, when this gets there, there will be a peak. This goes there, there's a peak. So as each of the components gets into the detector, let me start the video all over again. So let me start the video again. So your sample is injected. You can see the sample ejected. They are running through the column. And at different retention time, you can see this one is the one that is coming out last. As they are getting to the detector, a chromatogram is seen and everything goes into the waste. So you have your retention time for each of the components, and your peak area or peak height is proportional to the concentration or the quantity of your analyte of interest. So this is and it's typical Agilent HPLC. So your mobile phases are here. This is your degasser. Your flow rate is measured by the pump here. Your auto sampler is there. Your column is sitting in an oven, and your detector is at the end. And from the detector, it goes into the waste. So different applications, for example, if you are looking at acids, a weak acid or bases, you use the reverse phase. And these are the stationary phase that you use, C18 or C8, cyano or amino. And your mobile phase, remember that if your stationary phase is non-polar, your mobile phase must be polar. So you can use water, organic modifiers. If you are looking at ionics, bases, and acids, the mode is ion pair or ion chromatography. These are your stationary phases that you can use, and your mobile phase. Normal phase, your stationary phase will be polar, can be silica, amino, or diol, and your mobile phase will be non-polar. For ion exchange, you use the ion exchange resin, and your mobile phase will be aqueous buffers. Then for high molecular weight compounds, we use size exclusion chromatography. Then most times we use normal phase for compounds that are not soluble in water. So HPLC applications, HPLC can be applied to analysis of environmental samples. You can look at polyaromatic hydrocarbons, inorganic ions, herbicides, pesticides, flame retardants, and additives. We also use it for clinical analysis. You can analyze for amino acids, vitamins, proteins, because these are large molecular, they are macromolecules that HPLC, that GC cannot analyze. We also use them for analysis of consumer products like your pharmaceuticals and personal care products, for lipids, antioxidants, drugs, and sugars. So use it for pharmaceuticals, for controlled drugs, and maybe illicit drugs. We use them in biosciences for analysis of your nucleotides, peptides, proteins, your DNA. You can use them for your proteomics and genomics, and also use them. So it has a wide application on like your GC analysis. So that brings us to the end of CHM 408, my part. Has Professor Lanyika finished her part as well?
No, ma.
You are still having to